Okay, folks, this is a What the Physics video. This is about momentum, specifically linear momentum. And of course, we have our lovely learning targets. Today, we're going to be addressing this first one. I can use momentum and impulse equations to solve for desired variable. And later on, we'll talk about conservation of momentum, as well as, of course, the coolest part, I think, recognizing, applying momentum, impulse, and conservation in real-world scenarios. But right now, actually, this is a real-world scenario right here. Who has ever driven a car? You say, well, yeah, most people in the class, I assume, have, or at least considered it, taken behind the wheel. I don't know. So, how big is your car? You say, oh, I don't know, a big car, a little car. Just think about how big your car is and how well it handles. So, in other words, this is usually where I'd say, like, okay, class, who drives a big car? And people are like, oh, yeah, I drive an SUV, I drive a minivan, I drive a whatever. I'm not expecting people to say, oh, I drive an 18-wheeler. Okay, but still gets across the point. So, the small cars can be like little Volkswagens, little Jettas, compact cars, all sorts of different things. The point is, I'm asking you which car handles better. And by handles better, I mean which one can accelerate, speed up, slow down, change direction, which one can do that more easily. And most people, I think, would say the smaller car. Now you say, well, fair, I haven't actually driven a bigger car, so how am I supposed to know that one? Okay, imagine when you are driving. You say, well, fair, I haven't driven it before. Okay, fine. Imagine being in the front seat of a car, the passenger seat, while someone else is driving. If they're coming up on like a two-lane, you've got two lanes going in the same direction, and there is a truck in one lane, and then the other lane is empty, you're obviously going to go into the other lane, the empty lane. You say, well, of course, anyone's going to do that. That always happens, right? Even if you've got like just one regular car in the right lane, you're going to go to the left lane because it's empty. That is true. And in fact, quite often, if there are several cars in the right lane, that's when you go to the left lane or vice versa. But I'm saying specifically for a truck or a bus or something, some large vehicle. Most people do not like to be behind large vehicles. You say, yeah, it really makes you uncomfortable. Well, that is true. But what I'm getting at is here, it takes them a really long time when they're, let's say, stopped at a stoplight to get going again. Now, of course, it takes any car some amount of time to get moving, and that's why people don't like to sit behind a long row of cars when they're trying to get moving. But it seems like a truck takes that much longer. So imagine that you are in your little Civic and you're at a red light with a truck next to you. You say, all right, let's rev your engines. Who's going to get through first? And yeah, undoubtedly, it's going to be the smaller car. Not that the truck driver is not trying to get through, it's just that the truck has huge amounts of mass. Now, technically, the engine is bigger for the truck, but it's still going to take a lot longer for the truck to get moving than the little car. Okay, and you think about this in bad weather conditions. You say like, oh, how do you feel about driving next to a big old truck? And it's like, oh, it's scary, right? Not because truck drivers are bad drivers. In fact, they probably have a lot more experience than you would. But just the idea of one of these cars just coming over and knocking into you would totally crush you. It has a huge amount of mass, a huge amount of inertia. It's also got this thing called momentum. We'll talk about that in just a second. Okay, so let's say you're at your intersection and you zip on ahead and you really wanted to get ahead because the two lanes goes down to one lane and up ahead, and you do not want to be stuck behind this truck. So here you come up on the road construction, you get ahead into the lane of the truck. You're like, haha, yay, I win. And then you you go over this hill, and then what do you see directly ahead of you? You see brake lights. You're like, oh no, you slam on the brakes. You slam on the brakes and you stop just in time. You're like, wow, it's a good thing I stopped just in time. I am safe. Then you realize, am I safe? There's something that I should be thinking of. Then you look in your rearview mirror and you realize that is not Optimus Prime right behind me. So now you're in for some real problems because the truck is going to smash into you. You say, well, why is that? We already said the truck driver is not being a jerk or is not trying to cause any problems or anything, but the truck just can't stop in the same amount of time, the same amount of distance. And the reason for that is because of the truck's mass. So we've dealt with mass before, we've dealt with velocity before, but we haven't really put them together. So moving objects have velocity. We know that from Newton's first law, objects in motion stay in motion, at rest stay at rest, unless acted upon by a net outside force. Okay, sure. And moving objects also, of course, have mass. And the more mass there is, the harder it is for the object to accelerate, assuming a fixed amount of force. So if you compare our Civic versus Semi, our tractor trailer, then you say, oh wow, mass really is important. Mass really is important. So, okay, mass and velocity. Maybe if I combine these somehow, mass and velocity, combine powers to form Captain Planet. Wrong slide. Okay. And right now I'm sure like at least half the class is like, oh my gosh, Captain Planet, oh my goodness. No, really, probably like one person out there saying like, oh, I used to watch Captain Planet. People are like, I got nothing for you there. I don't even know what's going on here. Okay, fine. It was a fun cartoon show. They combined powers to form Captain Planet, and Captain Planet would fight against pollution and other things like that. Okay, so no, really, they combine to form momentum. Momentum is mass times velocity. First weird thing about momentum that you need to know is the symbol for momentum is the letter P. The letter P, that's so strange. Well, remember, it's mass times velocity. You can't have the symbol for momentum being M, because then it would be M is equal to M times V, and that just doesn't work. So why is it P? I don't know, that's not really the point. But it's not M. A little known fact, actually, though, physicists had actually considered changing the name of momentum to something else. Now, it's been around for centuries. Obviously, it didn't change, or we wouldn't be having this entire conversation. But runner-up names for momentum were Larrymentum and Curlymentum. So yeah. Ho, ho, ho! Oh, fair. Momentum, Larrymentum, Three Stooges. Oh boy. Oh boy. So here's my equation. Mass times velocity, and then the units are kilograms, meters per second. Nothing really special. Just the units for mass, and then the units for velocity. Okay, good stuff. Impulse. Impulse is, I think, a little bit more interesting. Impulse is when we're saying, okay, we know force is equal to mass times acceleration. And I know acceleration is delta V over delta T. All right, good stuff. So what I can do is I can say force is equals mass times acceleration. I can also say force is equal to, take out the A and put in the delta V over delta T. All right. Now you multiply both sides by delta T and you get impulse. Ooh, impulse. Yes, what is impulse? What does that mean? What? Okay, so impulse is not just how hard you're pushing. It's not just force, but it's for how long you are pushing. So if you're trying to move some stuff around and you push with a gentle force, if you push for a little amount of time versus a long time, that's going to be a definite difference in your impulse. Now you can also vary up the force and that'll change the impulse too. We'll get into more of that later on with the applications. But just recognize that impulse is force times time. Now, if impulse is force times time, then it stands to reason the right side of the equation is also going to be impulse. Well, that would be the m times delta v, because we multiply delta t on both sides. So F delta t equals m delta v. And that equals delta p, because remember p is equal to m times v, right? So delta p is equal to delta m times delta v. But we don't really change the mass, so it's just m times delta v. You say, okay, no, that's cool. That's cool. I get it. I'm good. So impulse, change in momentum. Units for impulse, Newton seconds. Newton seconds. Okay. Now, to make sure we understand what's going on here, let's do a little compare contrast with momentum and impulse. So momentum is mass times velocity. Momentum describes an object. I'd say, oh, look at that object going by. That object has a certain amount of mass, a certain amount of velocity. So you say, oh, that person going by has this much mass, this much velocity. That car, that whatever it is. Mass and velocity is describing the object. It's like discussing the properties of the object. The units for momentum would be, as we mentioned, kilograms times meters per second. You say, okay, no, that's good stuff, good stuff. All right. Impulse is definitely related, but not the same thing. Impulse is F delta T. Impulse is M delta V. And impulse is delta P. It's all three of these things mean impulse. It just depends on what information you have. If you have the force and time, if you have the mass and change in velocity, or you have the delta P, whichever. And you can also, of course, set them equal to each other too. But impulse is not describing the object itself so much. It's describing an event. So maybe you are pushing on something for a certain amount of time. Or maybe you're talking about an object as it speeds up or slows down. You say, oh, so you're describing the object? No. You're describing what is happening to the object, the event. And the units are Newton seconds. As we see, it's just the units for force times time, right? You say, well, yeah, but what about mass times delta V or delta P? Ah, that's interesting. So we know that newtons is actually kilograms times meters per second squared, right? Right. Parentheses. And then, of course, we have seconds here. And if we multiply these together, you say, oh, this is going to be weird. Kilograms, meters, seconds divided by seconds squared. Oh, I bet some of the seconds cancel. Yes! If you'd like, we can put this over a 1. That makes it easier. Seconds, and then the square cancels out. So I'm left with kilograms times meters per second. Oh, wait, that sounds familiar. Oh my goodness! Oh my goodness! Wait, is impulse the same as momentum? No, but they're definitely related. They have the same units, but that doesn't mean they're the same concept. Same units, but not the same concept. You say, well, how can they have the same units but be a different concept? Well, let's say my goal is to be a little bit healthier. I want to lose weight. I want to lose, say, 10 pounds. Okay? That's my change in weight. You say, wait, you want to weigh 10 pounds, Fair? That doesn't make any sense. I didn't say I want to weigh 10 pounds. I want to lose 10 pounds. My change in weight would be 10 pounds. Not my final weight, not my initial weight. So, okay. So my change in, like the impulse, but my change in weight is going to be the same units as my initial or my final, my momentum, right? Okay, so of course they should have the same units. Doesn't make sense not to, right? Right. So be careful. Impulse and momentum are definitely related, have the same units, and the units are interchangeable, but the concepts themselves are not interchangeable. And to get that point across, here we go. Which of these have momentum and which of these have impulse? So let's just do one first. So you are sitting in your chair. Let's make a little list here. P, and then delta P, momentum and impulse. Do you have momentum sitting in that chair? Let's see, momentum is mass times velocity. I have mass, of course, but I'm not really moving. So I'm going to say no. No, I don't have momentum sitting in the chair. Do I have impulse? Let's see, impulse is a change in momentum. So just because I don't have momentum right now doesn't mean I wouldn't later on. Is there any events going on? Or is there any net force on a certain amount of time, a change in velocity? No. No, 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 no. So no and no. So there we are. NN. And then I would go through the rest of these. And what I would like you to do is go ahead and pause the video and run through these and say, I think this one has momentum and this one has impulse and this one doesn't have momentum but it has impulse, so on, going through. So pause, unpause. Okay, here we go. Let's go through and check your answers. Mary, who is walking down the hallway, does Mary have momentum? Oh, she's moving and she has mass, so yes, she does have momentum. Does she have an impulse? Well, it doesn't imply anything about speeding up or slowing down, so I would say no, there's no real impulse here. Okay, so yes to momentum, no to the impulse. Okay. Brian, who hears the tardy bell and starts to run the physics class. Well, he's moving, he's got mass, so he's got momentum. Is there an event? Is there a change in velocity? Well, yeah, he starts running, right? I don't know if he was moving or not initially, but he's definitely changing up now. So yeah, there's momentum and impulse. Good. How about this? A pencil falling off the desk. You say, all right, pencil. Okay, is there momentum? Well, it's moving and it's falling, so yeah, sure, okay. Do we have an impulse? Well, falling means accelerating due to gravity, so we're speeding up. So yes, my velocity is changing. So I do have an impulse. Or you could also say, hey, there's a net force acting on the pencil. Okay, sure. For a certain amount of time, that's going to be impulse. Okay. Oops. A car coming to a stop. Okay, well, does it have momentum? Well, if it came to a stop, that means it doesn't. But at some point it did, so argue. Yeah, I'd say it has momentum at some point, yes. Does it have impulse? Yeah, it was slowing down. There was some braking force going on. So yes. A bird sitting in a tree. Well, bird sitting in a tree, if it's just sitting there, it's not really doing anything. It has mass but no velocity. So I'd say no. I'd say no to the momentum. Does it have any impulse? No, there's nothing really going on. It's just chilling, right? Okay, so no and no. Next, a ball getting kicked. Well, let's see. Is the ball initially moving? It didn't say. Well, is it moving afterwards? Well, it doesn't say, but you would imagine if it's getting kicked, there must have been some change in velocity going on. Maybe it wasn't moving initially, then it is. Maybe it was moving and now it's not. Or maybe it's moving the whole time, you just changed the direction or the speed. I don't know. But yeah, I would say there's momentum in there somewhere. There's going to be some momentum in there somewhere. And there was a change in momentum, so you could say yes, question mark. You know, it depends on when you're discussing about the momentum. But yeah, there's definitely an impulse. And then finally, a wooden board receiving a judo chop in a very exciting physics demonstration. So is there momentum? Well, maybe the wooden board is just chilling there first. I don't know. But after the judo chop, yeah, I'm sure that board is going flying, right? So there was an event, there was a change. So yeah, maybe there's momentum to begin with, maybe not, I don't know. But there's definitely a change in momentum. So that means, yeah, there was momentum at some point, and there's an impulse. Okay, a change in momentum. So going back to the original learning target, if you recall, I can use momentum and impulse equations to solve for desired variables. I am going to be rearranging these equations and solving for force. I can solve for the change in velocity, as I was just saying. Okay, and you just plug those into the equation and work through. But much more exciting, I think, is the recognizing and applying momentum impulse to the real world applications. Physics.